let's say the latency of a particular endpoint in our app, the index page or something, over the past 24 hours, when I see this line, I imagine that the data is actually tracking this line pretty closely. Like, oh, this is good. This is like exactly the data we want to be underlying this average line, but it could actually, in real life, okay, it's a little bit noisier. That's fine, we accept that. But something kind of interesting about averages is they really squash stuff together, and so they can actually basically invent new data points that didn't exist before. And so in this case, if we have something that's like a bimodal data set, so okay, maybe there's like the cached index page and the uncached index page. Cached is a little bit faster, lower latency. Uncached, and well, actually these are pretty close together, but whatever. There's actually two different sets, and what we're describing is this user experience that never actually happens to anybody. So that starts to get a little bit weird, and as your data becomes more and more multifaceted and complex, this problem kind of starts to manifest even more. And so, okay, well, averages, where you talk about that so much, everybody knows that percentiles is the way to go. And so, just kind of a little review of percentiles here. We've got some set of data, and okay, well, we're sorted. And the 50th percentile would be halfway through. So we go, 50% of the way through the list, and we call that the median, 90th percentile, and we've got our average there. And so in this case, the average and median are pretty close. This is uniform random sampled data between 1 and 20. So that worked out pretty well. Okay, so let's look at our latency using percentiles instead. And a really cool thing about this, by the way, is these make a very good guarantee. The average doesn't tell us anything. You might say, okay, the average, that means 50% of it was faster, 50% was slower. That's not always going to be the case. But we know with the median, the 50th percentile, that's like its definition. 50% of requests happen at this latency or faster. 90th percentile, 90% happen at this latency or faster. And so now we've got something that we can kind of reason about user experience. So let's say our 95th percentile of latency is X over the course of the past day. Well, okay, what does it look like underneath X? Let's say X is like 6 seconds. Well, I really hope that the 94th percentile is like 1 second, because that would be awesome. It would be very different than if the first percentile was also 6 seconds. That would be bad. So we can throw on another percentile here and start to flesh this out a little bit. Now we're starting to look at, okay, upper and lower bounds on experience, and there's something interesting in this contrived yet not so contrived example. And on a brief digression, we're looking at some real data at the end of this to prove that it's not just all keynote slides. And so, if we look at this, we start to see something interesting is going on. And so again, turning on the lens of our imagination and thinking about what's likely to be underlying these 2 percentile lines that we're looking at, this is kind of what I'm imagining, that it's a little bit noisy. We've got this spread, and then at some point things got a little bit slower, and so even but it didn't impact our top end. It was just the low end. I don't know how realistic that is. I think that this is something we might see more in web data, where we've got kind of 3 populations, and if you color them, it's easier to see. We've got fast requests, medium requests, baby bear requests or whatever, and slow requests. And these ones stopped happening. Whatever API endpoint was getting hit by somebody's script that was super optimized stopped getting hit. And so what that means at this time, if we put on our average latency would go up because we had fewer fast requests. Well, that's kind of weird. That it looks like things got slower because we're serving fewer requests and less load. Okay. When you start to have these multiple populations and you roll stuff up, things tend to get a little bit weird that way. And this is like one of the main reasons that computers are hard, that they're doing so many different things at the same time. So we rarely have a single distribution that's actually underlying what we're trying to measure. There's like multiple code paths for every endpoint. There's different users making requests to web applications, and they have different profiles with different amounts of data. Their sessions might be cached in different places. It's different requests for different resources being served on different instances, so different compute resources. And at different times of the day, different things are going on in the system. And so all these things that we're thinking about with percentiles even, where we're kind of imagining for this normal distribution type world, can actually be a little bit weird. And so, what if our data set actually looked like this? We'd have the same median and 90th percentile that we looked at before. There's actually only 2 values. So, again, manufactured, but this turns out to be something that's kind of hard to see in web data, and it's the distribution that's really interesting. And so it's not just that is there a single distribution, multimodal, not multimodal, but it's also not normal. It's abnormal. And specifically, this is like the classic thing that we'll see for web performance data. This is latency of background worker process monitoring a website. And we can see that, and this is very typical, there will be some population of requests that's fairly fast. In RUM data, this is like the 500 case, like, oops, okay, these are the errors, it fails out quickly. And then we have this kind of long tail curve that goes up and to the right, and if we plot it on a log scale, so here's our median, mean, and 90th percentile. They're actually kind of sorted pretty well in this case. But if we plot it with a log scale, this is the same data, but now we've got kind of that normal distribution with this little add-on for our errors there. And so there's actually a kind of front-end end-user experience monitoring company called Log Normal, which is named after the log normal curve, which is what we're looking at here, where it becomes normal when you apply a log to our kind of histogram. And by the way, I didn't explain this at all. In this case, we're looking at the distribution of latency. So we've got latency on the x-axis in microseconds, and frequency on the y-axis. And so what we're basically saying is, when we're starting to get into milliseconds, we're on the order of like 200 requests in our sample size that were about that fast, and it goes up to kind of 1,200 in our peak bucket. Looking at slightly different web performance data here, we start to see like really some of the challenges in the long tail where all of our data is clustered in these kind of bottom buckets, but really the long tail goes up to kind of orders of magnitude higher than what we're looking at. And so to kind of understand this, here's the log scale plot again. This is for AppNeta's blog, which is WordPress. So WordPress does work to generate pages unless you're using full page caching, in which case it does basically no work at all. And so we don't have that many blog posts, we're pretty good at caching. This is our deepest bucket by far, and then there's work, and there's some order of magnitude things when WordPress is doing whatever WordPress does. And so, the average for this is going to be kind of weird because it actually, did I put it on here? Yeah. Our average is there, and so that is some of the work, but our median is actually like right here. This is like what almost always happens. This is kind of the user experience, and then there's, okay, maybe that happens, but this never happens. There's never pages that are that fast, but also that slow. So this is, if you follow the drill down from Wikipedia, you can find a picture like this, which is basically the smooth curve version of what we just looked at. And I'll talk about this more a little bit later, but the bucketization here is really dangerous because if you imagine that we just had like one bucket that spanned from there to there, we wouldn't be learning anything from this. So the curves are continuous distributions are kind of preferred in some of these, like in literature, you'll see CDFs, cumulative distribution functions, which are the hardest to read visualization I think that was ever invented. So there's none of those in here, but that is what the experts advise for looking at distributions of data. And so here's kind of, again, stolen from Wikipedia, a little bit of a sense of what happens as the tail becomes longer and longer. In this case, the mean is in blue, and we can see that the mean, median, and mode are all looking great as long as you're pretty normal of a curve. But when we get this long tail version, our mean starts to slide out farther and farther because the average experience is being distorted disproportionately by outliers. And so what you see, and here's kind of a screenshot from a report we sent out to our customers, this is actually shockingly common. The average latency can be higher than the 95th percentile for poorly performing applications, where their outliers are bad enough that, okay, the average is like, wow, what does it even mean? It could be like the 96th percentile, the 99th, I'm not sure, but it's pretty wild. So I'm not saying this is the common case, but it's not uncommon either. It's really scary. All right, we've been looking at these numbers, and I complained about all of them. Can't be satisfied, only the most complex analysis. So how can we try to make sense of web performance data? Well, these abstractions that we started with weren't that bad. They're actually pretty good because they told us what was going on, and we could work from that. But histograms were really pretty helpful because we could see the distribution. We could understand, okay, there are two cases. These ones are getting, cache hits, and these ones are getting cache misses, and that's actually what's going on. And so these ones have one speed, these ones have another one, even though for the access log maybe they look kind of the same. Histograms let us see how frequent each value is. And so if we were to look at this guy with a histogram and sheet and color it, you'll see that these histograms basically are like combinations of different log normal distributions. Like you kind of stack them on top of each other. And so we've got population A, population B, population C, and they're basically kind of stacked on top of each other. There's like an interesting diagram I've seen where it was like if you look at histograms of people's height, and you see kind of like a two-peak thing bimodal, and then you break it down by gender and overlay it. It's like two like normal curves that are like making like McDonald's arches, right? That's basically what happens with all these multimodal things, except of course computers aren't normal, right? And so that worked out really well for this data. We could see what was going on. We've got 3 different populations with each with kind of their own experience, but from an operations perspective, it's very dissatisfying because something changed during this part of the day. That could be very interesting to us from a business perspective. Maybe it means that something's failing, maybe it means that something's timing out, people are having a worse experience, we want to know about it. And this graph didn't tell us that because when we made this histogram, we bucketized it across all time. And so how can we have a histogram where we're looking at the difference in value over time? And so with a lot of work in Keynote, you can make something that looks like this. And it's also really hard to read. And so basically what's happening in this picture is we've got our histogram, and then maybe it changes over time and some of these bars get lower, and you need like an ActiveX plugin to look at this, but that's okay because we're actually this is in IE9 right now. So it will run, and so we can kind of pan and zoom a little bit, yaw, and figure out what's going on. But this isn't that great, and the good news is some people thought about solving this problem a while ago, and what they came up with is something called heat maps. And so we've seen this on like maps for like crazy eggs data about like where you're clicking on the screen and stuff like that. Basically, the idea is we're using up 2 axes right now, one for frequency, one for value, and we've got these bars. Well, maybe we can be a little more efficient if we used color as kind of a virtual third axis. Then we can actually have a sense of how tall each of those bars are, and then build out something that changes over time. And so each slice of a heat map, the way to think about it is basically a histogram that we squashed. And so we can see we've got kind of our 3 populations, and then suddenly this guy stops occurring for a little bit. And so the rest of it fairly consistent. We've got these striations, these bands indicating different performance. And so now what we can do is visualize the distribution of our performance data over time. Now, RRD tool won't do this for you, but it's not that hard. It's possible to get your data into this format and be able to visualize heat maps. And so what we're going to do now is look at some real-life performance data in heat map form. So we got to look at a lot of lines that I made up, but they were heavily inspired by real life. And so kind of jumping right into this, a couple of years ago I set up a little instance of open source Reddit that I wanted to run load tests against, just to generate some interesting performance data. And when you install it out of the box, it's not really optimized for performance, right? Because Reddit goes down all the time. And so, so what we're looking at here is kind of average latency and the load average on the box increasing. And load average only gets to 1, which I'll explain later. But it's basically increasing linearly as we throw more requests at this thing. And you can't really make out the colors, but it's actually broken down by time spent in each layer of the stack. And where it's really growing is time spent queued in the web server. And so you look at this average latency and you're like, oh, the average user experience is getting worse. But actually, if you look at that in heat map form, these requests are getting queued in the web server, right? So the queue is getting deeper and deeper. The requests are getting processed at the same speed, but they wait longer in line every time. And so actually, it's not the average that was going up, well, I mean, the average is going up, we can see that, but it's not just the average, it's the min's also going up. So we've kind of, you know, we're basically, it looks like we've got this kind of stair steps going up and to the right, and it's pretty different to think about your average latency getting worse versus your minimum latency getting worse. And this is under constant load, right, here we go. But you know, it can't sustain that throughput, and actually, it turns out there's just like a single Python process that you know, okay, you install Reddit, it's a dev server, there's just one Python process running, and so it can only do one at a time, and so of course it's gonna perform like this. What did you expect? Okay, so let's look at some real world data here. Again, we've got an average. This is over the course of a week, so we can see, okay, this makes sense. This is like my website. When there's more people using it, it gets a little bit slower, and then nobody uses it at night, you know, in my primary region that I'm targeting, and it gets faster because there's less contention for the database or whatever. That's a great hypothesis, but it's not actually true for this data, even though we're looking at a single endpoint here. This is an endpoint that actually seems to have basically kind of 2 or 3 different patterns of data. So the average, maybe you can see, it's a little hard to see, is overlaid here as a red line. This is what we were looking at before. And there's consistent kind of, you know, baseline striation here. And then we've got these clusters of outliers that seem to kind of go up. And then if you look at it, this is actually a midnight align. So okay, something suspicious is going on at midnight every day. Well, if you dig into it a little bit more, it turns out that, okay, even though it was a single endpoint, we weren't really sure what we were looking at, and actually it serves both GET and POST requests. Okay, that's kind of a clue because it looks like there's a lot of requests here. If you were up there, it's about 80-20 Pareto distribution. That's convenient. Okay, well, you know, so if you look at it, this segment of requests is exclusively GETs, and then if I go the right way, that stuff up there is almost exclusively POST and a couple slow GETs because long tail. So basically there's like a floor on how fast our posts are going to be. So they're all up here somewhere. And then the GETs can be pretty fast, but they can also be really slow too because computers. And so in this case, what looked like, okay, it's an endpoint, you know, it's slower, the database, something, is actually, well, there's 2 different workloads. And there's something else going on here where one of the 2 workloads gets linearly slower throughout the day as it accumulates more data, and then it gets rolled up, and if you put on the disk latency here, it's like a big spike at midnight or whatever, because the database is like trying to do its roll up. So, so this is a case where, okay, you know, I pull out the access logs, and these look the same, but it's actually a little bit different. Here's another one. It looks like the same trick. It's we're actually looking at memcache data this time though, so. That's why it's so fast. This isn't just a really great web application, it's memcache. And so this makes sense again as we get more load in the middle of the day, requests get slower. And in fact, there is no trick this time. Really, it actually is getting slower. And so we have this very beautiful dense heat map, you know, probably a couple million requests over the course of the week. And you know, we've got our average again here in red. And you know, this nice kind of, you know, long tail, and we can see that it gets denser during the day. There's more requests going on, but there's also more slow requests going on at these times. Now, we looked at those long tail graphs before, and everything was kind of squashed on one side. How are you showing these heat maps that are actually full of data? Like, are these systems so well bounded that like the slowest memcache call is 30 milliseconds? You know, help me optimize my memcache. And I can't, because we're only looking at the bottom 98% right now. And this is what we actually do with our heat map visualizations by default. There's not like a secret behind that number. It just turns out that 98% is like pretty good for a lot of endpoints that you will see, you know, pretty dense data in the bottom 98%. And so you might want to adjust this and play with it. If you zoom out all the way, the entire thing that we were looking at before is now in the bottom row of our heat map. So this is like that histogram bucketization, like warning, like all of this richness, all this information. Like you can see kind of these bands, which actually turn into like different operations, like gets versus sets or something. Okay, well now it's all here, so there's nothing to see. And, but here's the cool thing. Something happens at 3 seconds. There is an upper bound that's kind of magical, which is timeouts. And so it looks like we exceeded 3 seconds slightly a couple times, measurement, computers, something, but you know, these are the 3 second outliers that are kind of, you know, ruining our average in this case. They're like, I don't know, what's the math? Like, this should probably, well, it's actually not doing too bad, but this should probably be, our average should be like 2 milliseconds or something. Okay, so here's one that's kind of interesting, and this is from my friend and coworker's blog. This is the latency of curl requests coming out of a WordPress application, and it looks like some endpoint that they rely on. Maybe it's like the Flickr photo API, maybe it's Discuss, you know, maybe it's whatever that thing is that people use to check for spam and comments, which never works. You know, maybe that got slower right before Christmas. You know, more comments, more load. The service is bad. We should complain to our providers. But actually, there's kind of this new slow population that got added, or a couple of them. And well, I said it was WordPress, and WordPress is basically like a honeypot that you run out of the goodness of your heart to get hacked. And so when you look at those requests, they're all of these weird like Russian domains, and don't go to any of these because I don't know what would happen to you. You can type them, and this website, every time you loaded it, would hit these, and there was like some sort of ad spam ring or something, so it was like trying to generate impression. I don't know, but really sketchy stuff. And you know, it kind of looks like, okay, we're looking at curl latency. Our website got a little slower. Why did it get slower? Oh, we're spending more time in curl. That's weird. And it's actually just this new stuff that appeared, these super slow requests to super slow Russian websites that are part of this botnet. Okay. So in this case, there was like a new population introduced, and you can see this happening. You know, do a release and it changes the way some of the endpoints perform. Maybe it adds a new endpoint. If it adds a fast endpoint, it's going to bring your average down, even though the rest of your site was still just as slow. If it adds a slow endpoint, it's going to bring your average up. Okay, that's good. We like that. We like to know that it got slower. So it's just, you know, as you mix in more populations, there can be strange effects on what you're measuring, so you've got to be careful there. So that's all the kind of, you know, disaster porn that I have for today. If you want to see visualizations like that, we have a free trial and a free product that basically, in my mind, exists to generate those pictures, but it also does a bunch of other stuff like distributed tracing. So, yeah. Any questions, comments, horror stories? Yes.
It wasn't annotated, but I assume that all the heat maps that we looked at were at bottom 98?
Yes. Yes, I think they are. So, you caught me. Yeah, otherwise, I mean, there would be, you know, there's a lot of, well, so this one I actually zoomed out a little bit, right? Because the 98th percentile was a little bit, it was somewhere in this range. But yeah, this guy's a solid 98%. I'm like, wow, yeah, you picked it just right. No, 98% is a magic number. Because the stuff above that is really just a couple outliers that, like, you know, the JVM garbage collected. Sorry.
Right on.
Would it be that challenging to figure out the percentile to select automatically based on the I don't know, the deviation in the?
There may be ways to be smarter about it, and I'm open to that idea. One thing that you might think is like, oh, like, yeah, it's definitely something about the range. It's like, well, we'll just pick like where most of the data is. Like, say where 98% of the data is. No, wait, that's where we already were. How do we make sense of it? I don't know. That'd be really smart.
So there's also something to be said for consistency there. Like if you're basing it off of where you're seeing like some of the data and shifting it, that can mean like you log into the interface later and you actually see something that looks pretty different. We already see this problem with like stacked area charts. If you have that one outlier request that takes 10 times as long, it spikes the chart and suddenly you can't see any detail anywhere else on the chart anymore.
I just visually an indicator that something appeared above the top would be a way.
Oh
Yeah.
yeah, I showed that off on
Yeah.
all these.
But
Sorry.
no, but yeah,
It's
if
like,
it was a consistent line above, then you would sort of have an indication that like maybe your graph isn't big enough. But if it's only a few points, if it's pretty sparse where you're cropping the over, then it seems like you got it.
yeah. If this stuff is interesting, I said we're hiring. All right. Well, we could probably do questions in a more informal manner then, and subsequent discussion. don't know if we want to adjourn to extra pizza or t-shirts, but that's fine with me, and I'll be sticking around for a little bit.
So,
If you hang out here or hang out in the kitchen, wherever, I'll be around for a while.
so just one comment before people break up. Dan mentioned that we do have the free trial, so absolutely give it a shot. Of course, we are interested people who are doing web performance as a business. We think we have a really great product for you. We're not quite ready to roll it out as a promotion yet, but sometime in the next month or two, we're going to actually do a promotion for all local web performance groups, like across the globe, for a discount for our product.
How do you do data into that free product?
That's an interesting question. So it depends on the stack that you're running. We always have a monitoring agent that lives on the server, but if you're in Python, it's a Python module. If you're in Java, it's a Java agent. PHP, it's a PHP extension.
You just like dump data into it, just like play with it?
Not as much. Like, we don't have the facility for you to just send in your data. It's monitoring your requests, but you can just install us and then run whatever load generating tool you usually use for testing.
It's its own data. I would have said devs and RPMs, and a Windows installer.
Well, to be precise, it is an exe.
You're right, it's not an MSI. Okay. Cool. Okay.
So when you talk about multimodal phenomenon, you give it this the most simplistic example so we can understand about the male and female and the height. So in this web performance, you mentioned also different attributes that we can take out, like the post or the get, or
Yeah.
if you're like waiting. Are you providing the interface to infer that? I know these are tools and charts, so we can actually pull out the probable cause for some of these, but are there ones that you just put it in so people actually can check to see, oh, could it be that phenomenon or that phenomenon, or what are the things
Right.
that have
Yeah. So there's certain things that are always kind of mixed together. If you're looking at your average applications latency, that's across tens to like hundreds of thousands of different URLs and endpoints, and so that's one of the things we break it down on. But the other thing is that with kind of the interactivity of the heat map, and I kind of hinted at it here, you can actually just drag select these different slices and then find out what are the attributes that kind of make that unique. So this is like a widget I copy pasted from somewhere else on the page, but it's like what URLs were going here. Did we like if we looked at our memcache stuff, are these like the hits or the misses that I'm like drag selecting? Is this mostly gets? Is it mostly sets? Kind of what are the populations here? So there is some amount of like, we built this because we think that you should be looking at this broken down in a certain way, but it's also oriented around kind of discovery and stuff because all web applications are different. I mean, they have like the same problems. It's always the database, but but they're all different. And so the coolest thing is kind of exploring your own data and seeing what's going on under the hood in a little bit more, I don't know, rich of a way. So.
Do you also like trace like the node, like so if it goes from New York to San Francisco and it has all these links and latency control?
Yeah, if you have like a service-oriented architecture, so you have some sort of front-end presentation tier, and you're making calls to a back-end analytics service, and then it makes requests to some database. This is actually a problem I had in my last job. We had this like service-oriented architecture, and it was really fun when I was on the dev side, and then I got promoted to the ops side, and I thought that was the coolest thing. So you get to run commands in production, you can crash the site anytime you want. But the bad part of it was like, okay, well, we wrote the search service in Erlang, and it runs over here, and no, the pricing service was in Erlang, and it has like amnesia, so it's two nodes that like have brain meld, and the search service is in Java. That's what's in Java, 'cause it's always in Java. And then there's the Python spelling corrector, and then this other thing, the Ruby like multi-search thing. And so you have to keep all those things running, and it's a PHP app that's calling into all those, and they call into each other. And so it's like something is slow, something's white screening. Oh, we'll just tail all the logs and see which one is like moving the fastest or the slowest or something, whatever. But actually, in these distributed systems, the coolest thing is if you can follow the path of individual slow requests through them and see where the bottlenecks are. And so that's like doesn't really play into this. That's like one of these dots, like what happened there. And so that's the other cool thing that we do, I would say, or well, one of the other cool things.
So go ahead.
Well, I don't want to make this an advertisement for your product, but I viewed a few of these vendors who are in the space, like you mentioned Keynote or New Relic or Gomez, and And I can see your visualization. Is this your added value or your differentiation? How are you guys, positioning yourselves to be different from those?
Putting me on the vendor seat.
It's normally my job.
Yeah, well, so I think this is one of the big things. Our company overall, like, we're looking at application server-side performance, which is really, I mean, my interest. That's what I think is super interesting. I'm like a systems guy. But what we actually do is try to stitch together the full kind of end-to-end web request. And what that means is starting looking at what the browser is doing. And if it's a synthetic browser, we do a keynote-like thing, but we do it way better. And when it makes those requests and hits the server side of your application, you're like, oh, this AJAX call is so slow. Well, you can click through and find, the distributed trace, and then go through, that, all your different service tiers, all the way down to, whatever Oracle query or whatever. So, kind of stitching that together, the full stack, the heat map, it's another thing that I think is big. Yeah, I don't know.
Fair enough.
I'm not in a good vendor mode right now.
Fair
I'm
enough.
just thinking about that.
All right.
So we can talk more later.
So speaking of,
Oh, sorry.
How fast is it?
How fast is?
Your product?
What is our average
Yeah.
latency?
What kind of overhead do you add?
How long will it take to draw this chart? Is that what you're
No.
If I'm running
How much
a-
is that?
Yeah.
Oh.
How expensive is the instrumentation that you're
Yeah.
providing?
Not very. So for kind of, basically we have two different things that make very low overhead. One is just kind of designed to be that way. It's not a profiler. It's not like XHProf. But two, it's sampling based. And so what we're doing is basically automatically adjusting the fraction of requests we're looking at over time as your web application's load changes to get the minimum amount we think is going to provide statistically significant data. And so what we measure in terms of latency impact is less than 1%, and that's kind of like, well, a lot of requests it's actually 0. We're really close to it because like there's an if, and then there's the else for it, and it goes down the else. Okay, perfect. Nothing's going on for this request, and then some of them there is that small amount of overhead. I can compare us like that's another differentiator we think, by the way, is our latency. We've had some positive comparisons against other vendors in the space. So it's like StatSD actually, I would say, because we're actually firing UDP back. It's still close is one of the things we do.
so if I can ask a question that is not actually about our product, what do you see as the same way that this is like an extension of histograms? What would be the extension to this, and do I need Oculus Rift to understand it?
Well, so yeah, there's a lot of things that would be really tempting to add to this, right? Like when there are different populations, like different URLs, but we're showing a heat map with all of them. Why do you make me like drag select a little slice, and then you tell me what's in there? Why can't I just visualize that this band is qualitatively different from this one? And so it's like, well, do we need to then have some like red dots and some blue dots and then the purple ones, or where there's a lot of both of them? And I think you could do some Oculus Rift stuff around that, right? Like where it's somehow 3D, but then it's like, it's like this guy. Franken visualization is what we're headed for. So right now it's pretty, you keep it pure, but there's a lot of stuff that might be interesting to tack on. And if you're interested in like crazy performance visualizations, do you guys like look at what Joyent, like the performance analytics guys, they're like Brendan Gregg, Brian Cantrell. They have some like really cool dtrace-based visualization stuff, and they do heat maps. It's super cool, but also some other crazy stuff like flame graphs. And so I don't know, I try to copy what they're doing.
That's why from what you just said, if you would ever want to have those different colors, you can pull off the layer and just examine and put it back. And that histogram with the 3D, you could provide like the slides, and that's kind of like a heat map by the time you drop it down. The histogram in 3D, or like, you can make transparent, still confusing too many lines, and if you could drop the time series down, so they're going this way. So you could, because each slice is a different qualitative axis.
Right, yeah.
Yeah, so you could separate that to see it and put it back.
Oh, like kind of pull this out.
Yeah, like an accordion and
Just
pull it
one
down.
at a time.
Yeah, just so
Yeah,
you could
that
see.
makes sense. Like a diff between two different endpoints, maybe like kind of overlaid on top.
Yeah, so, yeah, if you want to still compare a different phenomenon to time, it's accordion falling down, so you can still see that time progression and you see the depth separated.
That's like which axis do you accord?
So, you have it like that, and they're going that way, the z axis. So you pull each row, each break down, like, they were going like this.
Yeah,
And
so
then
like, you guys must annotate the data points since the agent's doing it, right? So you annotate the other
Can you
data.
go back to
Yeah.
that, the history, or the 3D?
Yeah.
So yeah, if you can pull it down, because you want to see the individual features, right?
Yeah,
And if you
like
want to
page
compare
3 or
them,
something.
you can pull them down and see them, because right now they're,
This is like a minority report style visual.
yeah. And you still have the value,
Yeah.
so you kind of expose because now, yeah, so it's more like yet another dimension. Well, not exactly, because there's the same height, but it's almost like you're already visualizing panning that way, but they're pulled down.
So it's stacked.
Yeah.
Stacked
Oh,
heat
almost,
maps.
yeah.
That's just
So
describing
put it
how
like
fast the data
An
is.
incline?
Yeah, yeah.
So just as an anecdote, the company that we share office space with, Oblong, they actually were like a spin-off of the company that did like design the Minority Report interface. So I really want to get us to do a hackathon together so we can try something.
You want to give them your data and see what they come up with.
Yeah, exactly.
Yeah, it's pretty fancy what they do. Oh, another thing is, like, wouldn't it be cool to be able to see all the percentiles on this? Well, we could, spray a bunch of lines on it, but maybe it could also be like some sort of like gradient going upwards. Like, oh, okay, our 90th percentile is down here, but then it's up here when stuff gets slower, so you can track some of these kind of user experience measures. I don't know. There's a lot of stuff out there with performance visualization.
And it's also something where you could probably, like, you'll have a sense whether it's just comparing gets and posts of things which people might want to be aware of, and so like you pop it up and flag that, by the way, this has all the posts right at the top. Yeah, like, because like you guys are going to have a lot of experience with what the 90% problem cases are.
Yeah, and there's definitely some machine learning potential, I'd say, to discover stuff like that.
Yeah.
We're like, I don't want to talk too much about the company, but it's like we did all this work to gather all this novel data that's highly structured. So for each one of these points, you can figure out it was from this IP at this time, and it went through these tiers and made these queries. But that's like so much data, it's so structured. There's a lot of stuff you can mine out of it. Visualization is really just like, okay, we started with raw data, all those terminals, right? Okay, we don't like this, it's too much data. Next thing is to visualize it, but actually forget that, we don't want that stuff. Why should we have to look at a picture? Why can't we just know the answer? And the questions to ask, and know the questions to ask, because that's what we're talking about. Like, what question should I ask? Should I ask about gets versus pose? Should I ask about warm cache, cold cache? Can't you just tell me what questions I want to ask and then answer them? Then I can do my job. Yes, I think this is good. There's actually some cool stuff with like the auto correlation that some people at Etsy worked on. Do you work at Etsy? You're sitting next to
No,
us.
just
Okay. But yeah,
Yeah, we scale
Oculus
stacks.
and stuff.
You gotta look for Oculus and Skyline and GitHub. You can read about the.
Yeah, there are.
So that's kind of like telling you questions that you should have been asking. Like, yeah, how are these two lines correlated? Figuring out when things go wrong.
All right, well, thanks again, Dan. If you guys want to stick around, feel free. I'm sure we'll all be available to talk and answer questions. So thanks.